Okay, let's dive right into this. Welcome back to another explainer. I'm absolutely thrilled to guide you through a truly fascinating algorithmic journey today. We're looking at the longest subarray with sum k, going straight from brute force to optimal. This is a classic technical interview problem. We're finding the longest subarray with a specific given sum, which we'll just call k. But listen, we aren't just going to look at the final answer here. No way. We are going to trace the entire evolution of an idea. We'll start with the most obvious, brute force approach, and step by step, we'll level it up into a highly optimized masterpiece. If you really want to understand how to think about algorithms, well, this is the perfect place to start.
So how do you actually solve the ultimate algorithmic interview question? Well, the real secret here is that interviewers don't actually just want the final answer. If you just memorize the optimal code and spit it out, you're kind of missing the point. They want to see how your brain works, right? They want to watch you take a perfectly valid but honestly terrible idea and systematically identify its weaknesses to transform it into something brilliantly optimal. That evolutionary process, that's exactly what we're going to map out today.
All right, first up, section 1, defining the subarray problem.
So our core mission is to comb through an array of numbers and find the longest subarray that adds up to a very specific target summation. Again, we denote that as k. But what exactly is a subarray? The absolutely crucial foundational word here is contiguous. A subarray has to be a strictly contiguous part of the array. It's literally like taking a knife and carving out a smaller, unbroken physical piece from the larger array. Every element you include has to sit right next to each other.
And this actually brings up a really common trap that trips up a ton of people, confusing a subarray with a subsequence. Let's say you have an array with the numbers 1, 4, and 3. If you grab the 1 and the 3, but you skip the 4 in the middle, you've created a subsequence. But because you skipped an element, they aren't contiguous anymore, so it is absolutely not a subarray. For our problem today, every single element we add up must be physical neighbors. No skipping allowed, for sure.
Moving right along to section 2, the brute force trap. When you're sitting right there in the hot seat of an interview, your first instinct is usually the most obvious one. If we need to find the longest subarray that equals k, why not just generate every single possible subarray, sum them all up one by one, and just see which one is the longest? Well, here's the major problem with that instinct. Generating every single subarray means setting up an I pointer, a j pointer to mark the start and end, and then running a whole third inner loop just to calculate the sum between them. That leaves us with a devastating time complexity of O of n cubed. Now, sure, we could mathematically optimize this a tiny bit. By keeping a running total as our j pointer moves, we can drop that third loop and get our time down to O of n squared. But honestly, even at O of n squared, for massive data sets, this solution is still way, way too slow. Which leads us directly to the unimpressed interviewer. You know the one. You've proudly put your O of n squared or n cubed solution up on the whiteboard, and they just look at you and say, "Do you actually need n cubed for this? Can you optimize your brute force?" It's a terrifying moment, right? But it's exactly the prompt we need. We've proven we understand the basics, but now we have to fundamentally rethink our approach to speed this whole thing up.
Okay, section 3, hashing and reverse mathematics.
So we're upgrading from that brute force trap to a definitively better approach. To pull this off, we're going to introduce a data structure, the hash map. Our goal here is to keep a running track of our prefix sums as we move through the array, storing them in our map so we can look back at them instantly. So how do we actually use this for algorithmic detective work? Well, it's a little thing called reverse mathematics. Imagine you're walking through the array, adding up numbers as you go. Your total running sum right now is x. But remember, you're looking for a subarray that adds up to k. If you can just look backward into your hash map and find a point where the running sum was exactly x minus k, boom! That mathematically guarantees that the chunk of the array between that old point and your current position adds up exactly to k. You don't even need to calculate the middle. You literally just deduct the past from the present. But listen, we have to be incredibly careful here because of a sneaky edge case involving zeros. Imagine your array is 2, 0, 0, 3, and you want a sum of 2. As you move past those zeros, your prefix sum stays exactly the same. It just stays at 2. If you keep updating the hash map with the newest index for that sum of 2, you're actually shrinking your subarray. To get the strictly longest subarray, you absolutely must keep the leftmost index. If a sum previously exists in your map, do not re-update it. Keep the earliest record. That is absolutely crucial.
Let's think about the scoreboard for our better hashing approach. By avoiding nested loops and just doing hash map lookups, our time complexity drops beautifully down to O of n, assuming we use an unordered map. However, keep in mind, if you hit a worst-case scenario with hash collisions, it can actually degrade back to O of n squared. Also, because we're now storing all those prefix sums in a map, our space complexity jumps from 0 extra space up to O of n. Basically, we traded space for speed.
All right, section 4, the two-pointer optimization. Now, you might be wondering, can we do even better? Well, if our array only contains positive numbers and zeros, yes, we absolutely can. Think of this approach like a highly physical sliding window. We set a left pointer and a right pointer right at the start of the array. Then, we move the right pointer to expand the window. And because we only have positive numbers, expanding right guarantees our sum naturally increases. If our sum hits k, awesome, we record the max length. But if our sum exceeds k, we stop. We freeze that right pointer, and we start shrinking from the left pointer to trim the excess sum. We're just dynamically expanding and shrinking our window as we march across the entire array.
Now, you might see a while loop nested inside another while loop and immediately panic, thinking the time complexity is back to O of n squared. But actually, scratch that. It's not. It's O of 2n. Why? Because that right pointer only ever moves forward across the array, and the left pointer only ever moves forward to catch up. Neither pointer ever resets or goes backward. In the absolute worst-case scenario, each pointer travels the length of the array exactly once. N plus n equals 2n. It's brilliant. But here is the true victory of this two-pointer method. The real reason it's considered the ultimate power-up and the optimal solution. Because we're literally just sliding two integer markers across our array, we eliminated the hash map entirely. We're storing absolutely nothing extra. Our space complexity plummets all the way down to O of 1, constant space. So it's incredibly fast and completely memory efficient. Bringing it all together, section 5, acing the technical interview. We've completely and successfully modeled the exact evolutionary arc that an interviewer wants to see. We didn't just guess the answer, we engineered it. Let's recap our final scoreboard. We started off with brute force, surviving on O of n squared time but taking up O of 1 space. We noticed it was way too slow, so we evolved into the hashing approach, getting that blazing fast O of n time but sacrificing O of n space to hold our map. Finally, for positive numbers, we unlock the optimal two-pointer approach, maintaining incredible speed at O of 2n while reclaiming our memory efficiency right back to O of 1 space. But wait, before you confidently wipe that whiteboard clean, there is one massive caveat you absolutely must tell your interviewer. The greedy two-pointer method completely falls apart if the array contains negative numbers. Why? Well, because moving the right pointer is no longer guaranteed to actually increase your sum. A negative number shrinks it. So if the array contains negatives, you have to tell the interviewer that the two-pointer fails, and your hashing approach from earlier, that actually remains the undeniable optimal solution. And the whole shebang comes together perfectly right there. You've completely mastered the longest subarray problem from every single angle. But I want to leave you with one final thought to keep your algorithmic brain churning. We just figured out how to find the longest subarray that equals k, right? But how would you alter your code to find the total number of subarrays that equal k? Think about that hash map. Keep pushing yourself, keep optimizing, and I will see you in the next explainer.